In this lecture video, we look at multivariate continuous random variables and their distribution. Let x1 and x2 be random variables of the continuous type and consider them jointly via the two-dimensional or bivariate random vector x1, x2. Denote the two-dimensional sample space of this random vector by script A. Now suppose there exists a function f that satisfies the following two conditions. It evaluates to a non-negative number at all points in the plane, and for all events that are subsets of the sample space script A, the probability of that event is obtained by integrating this function f over the event of interest. If such a function exists, it's called the joint probability density function, or the joint PDF of x1 and x2. Now the CDF of the joint distribution of x1 and x2 is defined in the same way that it is for the case when x1 and x2 are discrete random variables, in the sense that the CDF evaluated at a point s and t is defined to be the probability that x1 takes on a value less than or equal to s, which is the first argument, and x2 takes on a value less than or equal to t, the second argument. But the way that we calculate this probability differs from the previous case because now x1 and x2 are continuous. And in particular, in order to evaluate this probability, based on the second bullet point on the previous slide, we have to integrate the joint PDF with respect to x1 and x2, x1 ranging from minus infinity up to s, and x2 from minus infinity up to t. And so that in the case of continuous bivariate random variables, we obtain the value of the CDF by integration. So this is the CDF of a bivariate continuous random vector, and hence its domain is r squared, the entire two-dimensional plane. And so when we define a CDF for a joint, for a bivariate continuous random vector, we need to make sure that this joint CDF is defined at every point in the plane. Now let's talk about expectation in the context of multivariate random variables, and then we'll look at some examples. So let x1 and x2 be random variables with joint PMF or PDF, lowercase f, and let g be some function of x1 and x2. In particular, g is going to be a real valued function of these two random variables. And so because g is a function of random variables, it itself is a random variable as well. Now the expected value of this function g, which is a function of x1 and x2, is denoted this way. And so this is not surprising since we've seen how we represent expectations for univariate random variables. So this is the expected value of the function g of x1 and x2. If we have discrete random variables x1 and x2, then we evaluate this expectation via summation. Okay, and again, the expected value of this function g is just a weighted average of the values taken on by g, and the weight factor is the joint PMF. If x1 and x2 are continuous, then we obtain this expected value via integration. In both cases, what it's calculating, again, is a weighted average of the values taken on by the function g, and the weight factor being either the PMF, if we're dealing with discrete random variables, or the PDF, if x1 and x2 are continuous. So for example, suppose that x1 and x2 are continuous random variables. The expected value of the product, x1 times x2, is denoted this way, the expected value or expectation of x1 times x2. And by definition, this is the integral. And notice that this integral is taken over the entire plane, the entire two-dimensional plane. The integrand is this function, x1 times x2, so it shows up right here, times the joint PDF of x1 and x2, the expected value of x1, all right, is given by this expectation, the expected value of x1. Now notice that this does not depend, this function g here, x1, this does not depend on x2, and that's perfectly fine. So we can calculate the expected value of x1, for example, using the joint PDF of x1 and x2. By definition, this is the double integral. So this is an integral over the entire two-dimensional plane of this function right here, x1. So x1 times the joint PDF. And finally, we could find the expected value of this quantity, x, the square of x2 minus its mean. Now you'll recognize this. This is the variance of x2. So the variance of x2, which is the expected value of the square of x2 minus its mean, can be computed in terms of the joint distribution, or using the joint PDF of x1 and x2. It's going to be the integral over the double integral over the entire two-dimensional plane of the function whose expectation we want. All right, and so we have that function right there times the joint PDF. Now, if x1 and x2 are discrete random variables, then we would do the same thing we did up here, except we would replace the integral signs by summations. Now let's talk about covariance. This is a very important property between two random variables in the context of multivariate distributions. And so let's take a look at this. So let the random variables x1 and x2 be jointly distributed. The covariance of x1 and x2, which will be denoted this way in these notes, cov of x1 and x2, is defined in the following way. It's defined in terms of an expectation. All right, so it's defined to be the expected value of the product of x1 minus its mean and x2 minus its mean. Now, there's a nice computational formula for the covariance. It turns out that this expected value, which is the definitional formula, is equivalent to this computational formula, the expected value of x1 times x2 minus the product of the expected values of x1 and x2. Now, this second expression is typically easier to compute, and so we'll often use that instead of the definitional formula. What I would recommend to you as an exercise is to check to see, make sure that you can derive this computational formula from the definitional formula. So that's the definition of the covariance. Now there's some nice properties of covariance that we need to know about. So let's take a look at these. So suppose that x1, x2, y1, and y2 are random variables, and let a, b, c, and d be constants. Then the following results concerning covariance hold. So the first property is that the covariance of x1 and x2 is equal to the covariance of x2 and x1. And so what that means is that it does not matter the order that we list the two random variables in the arguments of the covariance function. The second property is that the covariance of x1 with a constant is 0. In other words, the covariance between any random variable and any constant will always be 0. The third property is very useful. The covariance of a random variable with itself is the variance of that random variable. So this is helpful because it's often useful to decompose or to re-express, let me put it that way, to re-express the variance of a random variable as the covariance of the random variable with itself. Property 4, the covariance of linear combinations of random variables. So remember that whenever we're talking about covariance, we're talking about the covariance of between two random variables. And so in this particular property, we have two random variables, The first represented by this linear combination of x1 and x2. So a times x1 plus b times x2. That's the first random variable in the argument list for the covariance. And the second random variable in the argument list for the covariance is this linear combination of two random variables, y1 and y2. So c times y1 plus d times y2. And it turns out that this covariance can be decomposed or rewritten as in the following way. And this is very useful. A times c times the covariance of x1 and y1 plus a times d times the covariance of x1 and y2 plus b times c times the covariance of x2 and y1 plus b times d times the covariance of x2 and y2. Property 5, the variance of this linear combination of x1 and x2 given by a times x1 plus b times x2 is equal to and can be decomposed as a squared times the variance of x1 plus b squared times the variance of x2 plus 2 times a times b times the covariance of x1 and x2. So again, whenever we're talking about a variance, we're talking about a variance of a random variable. And in this case, we have a random variable that is given by or defined in terms of the linear combination of two random variables. And the variance of this linear combination is re-expressed or decomposed in terms of the variances of the constituent random variables and the covariance of those random variables, as well as the constants that are used in constructing the linear transformation. Now, if x1 and x2 are uncorrelated, then the variance of this linear transformation simplifies somewhat. This last term would drop off, and so that's given by a squared times the variance of x1 plus b squared times the variance of x2. Now, these last three results easily generalize or extend to more than two random variables. So we can have more than two random variables in the linear combination in any one of these positions. All right. Now we would have to tweak the results, but that's easy to do. Okay, now so what I would recommend is that you make sure that you can prove each of these 6 properties. Now let's define correlation. So let the random variables x1 and x2 be jointly distributed. The correlation between x1 and x2, which will be denoted this way in these notes, cor of x1 and x2, is defined to be the covariance of the two variables divided by the square root of the square root of the product of the variances. Now another way to write that is the covariance of x1 and x2 divided by the product of the standard deviations. Now, understanding and interpreting correlation. The correlation is a measure of the strength of the linear relationship between two variables. So, we're measuring the strength of a relationship, but not just any relationship. In particular, we're measuring the strength of the linear relationship between the two variables. The correlation between two variables is always between -1 and +1. So if you are computing a correlation as part of a homework problem or just in your own research, if you happen to get a value for a correlation that is less than -1 or greater than +1, you better go back to the drawing board. You know it's wrong because correlations are always between -1 and +1. Now, how do we interpret the strength of the linear relationship? Well, if the correlation between two random variables is 0, what that implies is that there is no linear relationship between the two random variables. On the other hand, if the correlation is either -1 or +1, the two extremes, that means that there is a perfect deterministic linear relationship between the two variables, and the nature of the relationship, being either negative or positive, depends on the sign of the correlation. If the correlation is -1, then there's a perfect negative linear relationship between x1 and x2, and if the correlation is +1, then that implies that there's a perfect positive linear relationship between the two random variables. Now, typically in real-world data, you're not going to see a correlation that's exactly equal to -1 or exactly equal to +1. But what we can say is that as the magnitude of the correlation increases, as the correlation gets closer to either -1 or +1, the stronger the linear relationship between x1 and x2. Likewise, the closer the correlation is to 0, the weaker the linear relationship is. Okay, so let's look at an example, example 45. So consider again the experiment of tossing 2 fair dice and recording the up faces. Let x1 and x2 be the minimum and maximum numbers shown respectively. So we have looked at this example. We have, in the last lecture video, we came up with the joint PMF and the joint CDF of this distribution. And so now we want to find the covariance of x1 and x2, as well as the correlation between x1 and x2. Now, using the formulas given previously to find the various expectations and variances and so forth, we have the following results. The expected value of x1 times x2 is equal to 12.25. The expected value of x1 is 2.5278. The variance of x1 is 1.9715. The expected value of x2 is 4.4722, and the variance of x2 is 1.9715. Now, with these values, we can compute the covariance of x1 and x2 using the computational formula. So the expected value of x1 times x2 minus the expected value of x1 times the expected value of x2. And so this is 12.25 minus the product of 2.5278 and 4.4722. And when we calculate that product and then take the difference, we get 0.9453. So that is the covariance of x1 and x2, the covariance of the minimum and maximum number shown when we roll 2 distinguishable fair dice. Next, we'll calculate the correlation. Now remember, to get the correlation, we divide the covariance by the square root of the product of the variances. All right? And so we'll do that on the next slide here. So the correlation between x1 and x2 turns out to be 0.4794. So that's a moderate correlation. Remember, the correlations range from -1 to +1. And some people like to set up categories for strengths of correlations or magnitudes of correlations. And in most of those categorizations, a correlation of 0.47 or 0.48 would typically correspond to a moderate correlation. Now let's move on to example 46. Let x and y be continuous random variables with joint PDF given by the following expression. So the PDF, the expression for the PDF is c times x times y if x is between 0 and 1 and if y is between 0 and 1 as well. For any other point x and y, the PDF evaluates to 0. So we want to graph the sample space of the bivariate random vector. We want to determine C. We want to derive the joint CDF of x and y. We want to compute a probability, the probability that x is greater than 1/2 and that y is greater than 3/4. We want to compute the covariance of x and y. And then finally, we want to compute the correlation of x and y. Now the sample space in this, or for this distribution, you can see from up here, the sample space is going to be the unit square. So if we were in class, I would either draw on the whiteboard or put something up on the overhead. We really can't do that here, but just on your own page, write down the coordinate axes, one for x and one for y, and then mark off the region corresponding to the unit plane, the unit square. All right, and so then to find c, we need to make use of the fact that the joint PDF, when integrated over the bivariate plane, integrates to 1. All right, and so we have this constraint that this integral over the two-dimensional plane of the joint PDF is equal to 1. Now this simplifies to the integral over the unit square. So x is going from 0 to 1, y is going from 0 to 1, of the expression that the PDF evaluates to over that unit square, which is c times x times y. Now, we can pull the constant c out, and when we do that, we can also note that the integral from 0 to 1 of x dx does not depend on y. All right, y being the variable integration for the outer integral. So we can pull that entire integral outside of the outer integral. So this is equal to c times the integral from 0 to 1 of x dx times the integral from 0 to 1 of y dy. Okay, and so then we can solve each of those integrals using the fundamental theorem of calculus. And so we get a value equal to c over 4. And so c over 4 is equal to 1, and so that implies then that c is 4. And so the fully specified expression for the joint PDF is 4 times x times y for values of x and y, where x is between 0 and 1, and y is between 0 and 1, and then 0 otherwise. Now we want to derive the joint CDF. Now this is where it's handy to have that picture that you drew of the sample space of the bivariate random variable. And so using that picture and keeping in mind that the joint CDF is accumulating probability over regions from a given point and then down and to the left, we can know the following. That the CDF evaluated at a point xy is going to evaluate to 0 if either x is less than or equal to 0 or if y is less than or equal to 0. Because at any such point, we have not yet accumulated any probability. The CDF is going to evaluate to 1 if both x is greater than 1 and y is greater than 1. The CDF at a point xy will evaluate to, or is equal to, the CDF evaluated at x comma 1 if x is between 0 and 1 and y is greater than 1. And then finally, the CDF evaluated at a point xy is equal to the CDF evaluated at 1 comma y if x is greater than 1 and y is greater than 0 but less than or equal to 1. So we get these values or expressions for the CDF just by virtue of looking at the picture of the joint sample space that you drew down a few minutes ago. Now, for values of x and y where the point is inside the unit square, that's where we have to do some work. Okay, and so for values of x and y where x is greater than 0 and less than or equal to 1, and also y is greater than 0 but less than or equal to 1, the CDF evaluated at such a point is given by definition by this integral of the joint PDF. If I can highlight that, it's not going to let me. But the double integral of the joint PDF, where, and then I've got variables of integration u and v, okay, that I'm using. And so u is ranging from minus infinity up to y, and v is ranging from minus infinity up to x. Actually, I just realized that I had the limits of integration, the order of the limits of integration switch. So I just fixed that in my notes. So what you're seeing here on the screen now is the corrected version. So in your notes, change your notes so that they look like this. So we've got u ranging from minus infinity up to x, v ranging from minus infinity up to y. So I just changed the order of x and y in these various intervals. All right. So anyway, you can see here that when we do this, so this is the definition. This is how we calculate the CDF evaluated at a point x and y, where x is greater than 0, less than or equal to 1. Y is greater than 0, less than or equal to 1. So the point x, y is in the sample space of the bivariate random variable. And so the CDF is equal to the integral of the joint PDF, where u ranges from minus infinity to x, again, the first argument, and then v ranges from minus infinity up to y. Now, this simplifies to the integral, the double integral, where u goes from 0 up to x and v ranges from 0 up to y. All right, and then once we're looking at that subset of the sample space, over that set, then the joint PDF evaluates to 4 times u times v. Now we can pull the 4 out of both integrals, all right? And then we can put parentheses around that inner integral, as we've done here. And then note that the inner integral, the integral of u from 0 to x, does not depend on v at all, so we can pull this inner integral completely outside of the outer integral, and so we have this product of these two integrals. We can then use the fundamental theorem of calculus to evaluate each one of these. And so we would have u squared over 2, evaluated at x and then 0, and we take the difference. Here we have the antiderivative v, which is v squared over 2, evaluated at y and then 0, take the difference. All right, and so we end up with, for values of x and y in the sample space of the bivariate random variable, the CDF evaluates to x squared times y squared. And so when we put these results together, we have this fully specified expression for the CDF, this piecewise defined function depending upon the values of x and y. So make sure that you understand how we came up with that and that you can come up with it yourself. Now we want to compute the probability that x is greater than 1/2 and that y is greater than 3/4. Now it helps to first draw a picture of the region over which we're going to be integrating. All right, and so we're going to be integrating over a rectangular region in the upper part of the sample space of the bivariate random variable. So the probability that x is greater than 1/2 and that y is greater than 3/4 is given by this double integral of the PDF, where x is going from 1/2 up to positive infinity, all right, corresponding to x being greater than 1/2. And then y is ranging from 3/4 up to infinity, again corresponding to y being greater than 3/4. But now this simplifies to the integral of 4 times x times y, which is the expression for the joint PDF over the values over the points in the sample space, where x is ranging from 1/2 to 1 and y is ranging from 3/4 to 1. And so again, we can solve this integral, this double integral, using an approach that similar to what we did before. All right, noticing that this inner integral does not depend at all on y, and so we can pull that thing out of the outer integral, and we end up with the product of two univariate integrals, and so we can use the fundamental theorem of calculus to compute those. And what we end up with is a probability of 21/46. Now, we can also use the joint CDF to compute this probability, and it really helps to draw a picture in trying to do this. The way that we would use the joint CDF in computing the probability that x is greater than 1/2 and that y is greater than 3/4 in the following way. So we know that the total area under the joint PDF over the sample space is 1. And so this probability is given by 1 minus the CDF evaluated at 1/2 and comma 1 plus the CDF evaluated at 1 comma 3/4 minus the CDF evaluated at 1/2 comma 3/4. So we're subtracting this value from 1. And so when we evaluate the CDF at these various points, this is what we get. And it turns out that using this approach, again, the probability is 21/64, which is exactly what we got by integrating the joint PDF over the region of interest. All right, now let's compute the covariance of x and y. So we're going to use the computational formula to calculate the covariance. Note first that the expected value of the product x times y is given by the following. So by definition, the expected value of x times y is equal to this double integral over the entire plane of x times y times the joint PDF. This simplifies to the double integral over the unit square of x times y times 4x times y. That's the expression for the joint PDF over the unit square. All right, and we can pull the 4 out, the constant out. We can combine terms, and so we have the integral here of 4 times x squared times y squared, and then we pull the 4 out. We notice here that this inner integral does not depend on y, so we can pull that out. And then again, we're here in the same kind of situation we were before, where we have a product of univariate integrals, which we can then use the fundamental theorem of calculus to compute. And so we end up getting 4/9, as you can see. So this is the expected value of x times y. All right, now the expected value of x is, by definition, using the joint PDF, the double integral over the bivariate, or over the two-dimensional plane is x times the joint PDF. That simplifies to the multiple integral, the two-dimensional integral over the unit square of x times 4 times x times y. And then we're off to the races again. We've got everything we need, all right? And so we can pull the 4 out and evaluate the double integral in the usual way. And this turns out to be 2/3, as you can see. Likewise, the expected value of xy is this double integral over the two-dimensional plane of y times the joint PDF. That simplifies to the double integral over the unit square of y times 4 times x times y, where both x and y are ranging from 0 to 1. All right, and so then we can solve this double integral in the usual way. And again, we get 2/3. And so the covariance of x1 and I'm sorry, not x1, but the covariance of x and y, which again, using the shortcut formula, is given by the expected value of x times y minus the product of the expected value of x and the expected value of y, is 4/9 minus 2/3 quantity squared, which is 0. Okay, then once we have the covariance, we can find the correlation. Now, we know that the covariance is 0, so the numerator is 0. The only question would be, is this correlation defined? If either of the variances are 0, then the denominator would be 0, and the ratio would not be defined. But because these, both the distributions, neither of the distributions are degenerate. They both have positive variance, and so we know that the denominator is not 0, and so this is defined, and so it turns out it's equal to 0. So the correlation between x and y in this for this distribution is 0, and so that implies that there is no linear relationship between the two random variables. Next, we're going to look at a slightly different distribution. This is example 47. So let x and y be continuous random variables with joint PDF given by the following expression. So the joint PDF evaluates to the quantity c times x times y for points in the unit square where x is strictly less than y. Now before we didn't have this constraint between x and y. All right, before they were completely unconstrained. X varied between 0 and 1, y varied between 0 and 1, and there was no constraint between them. There was no relationship between them. But in this case, we're specifying that x has to be less than y in order for this point to be in the sample space. And when that's the case, then the joint PDF is equal to c times x times y. For any other point, the CDF evaluates to 0. And so we're going to determine c. We're going to derive the joint CDF of the bivariate random variable x and y. And we will compute, again, this probability, the probability that x is greater than 1/2 and y is greater than 3/4. And then we'll compute the covariance and the correlation of x and y. So we're going to determine the constant c to make this a PDF. We'll derive the joint CDF of the bivariate random variable x and y. We'll compute the probability that x is greater than 1/2 and that y is greater than 3/4. And then we'll compute both the covariance and the correlation of x and y. Now the first thing we need to think about, let me jump back here, is the sample space of x and y. In this case, the sample space is not the entire unit square. It is the part or the subset of the unit square where x is strictly less than y. Now, if you'll draw this out on a sheet of paper, you'll find that this is the upper triangular portion, the upper left triangular portion of the unit square. And so it's useful to have that picture when we evaluate some of these integrals. So to find the constant c, we're going to integrate the joint PDF over the entire plane. We know that that has got to be equal to 1 because f is a joint PDF. And so when we do this, it turns out that this simplifies to something a little bit different than it did in the other example. Here, we have the integral where x goes from 0 to y, and y goes from 0 to 1. And over that subset of the sample space, the PDF evaluates to c times x times y. Now we can pull the c out front, and we're left with the integral on the inside, the integral of x from 0 to y. And now note that this integral does depend on the variable of integration for the outer integral. Right? It depends on y because the upper endpoint of the integral is y. So we cannot pull this out of the outer integral like we did in the previous example. So we just have to go ahead and integrate it right where it is. And so we use the fundamental theorem of calculus. The antiderivative of x is x squared over 2. We evaluate that at y and 0 and take the difference. And so that's what we get down here. And then this simplifies to an integrand of y cubed, which we're integrating with respect to y from 0 to 1. All right? And so then we use the fundamental theorem of calculus, and we end up getting an expression c over 8, which again is equal to 1. So that implies that c is equal to 8. And so the fully specified expression for the joint PDF is 8 times x times y for points in the unit square where the first coordinate x is strictly less than the second coordinate y, and it's 0 otherwise. Now let's find the joint CDF. We'll denote it by cap f. The space of xy consists of that portion of the unit square above the equiangular line, that upper left triangular portion of the unit square. Now in evaluating the CDF, there are 5 regions of the plane to consider. the points where x is less than 0 or y is less than 0, points in the plane where both x and y are greater than 1, points in the plane where x and y are between 0 and 1 and that x is less than or equal to y, points in the plane where y is between 0 and 1 but x is greater than y, and then points in the plane where x is between 0 and 1 and y is greater than 1. So we'll consider these regions in order. Now, if we're looking at the first region where x is less than 0 or y is less than 0, then we know that the CDF must evaluate to 0 because we have not accumulated any probability at that particular point. If both x and y are greater than 1, then we've accumulated all the probability there is to accumulate, and so the CDF at that point, or at such a point, evaluates to 1. Now, if we're looking at a point where both x and y are between 0 and 1 and that x is less than or equal to y, then the CDF is going to be given by the double integral of the joint PDF, and we're using u and v as our variables of integration here, where u ranges from minus infinity up to x, v ranges from minus infinity up to y. This simplifies to the integral 8 times u times v. Now I'm changing the order of integration here, so I'm integrating with respect to v first. And so v ranges in this case. Let me start with the outer integral first. So u is going to be integrated from 0, or ranges from 0 to x. And for a given value of u, we're integrating with respect to v from u up to y. And so if you draw a picture, I think it'll make sense why we're doing that. Okay, so now we can pull the 8 outside of the integral, and we look at the inner integral and we see that it does depend on the variable of integration for the outer integral, which is u, because u shows up as the lower limit of this integral. And so again, we have to integrate it in place, which is not hard. It's just a univariate integral. We use the fundamental theorem of calculus, and so we get the expression y squared minus u squared, which we have to multiply against u. And so using properties of integrals, right, distributing the u across that difference and then decomposing the integral of the difference as the difference of integrals, we get this expression here, this integral expression, which we can then solve fairly straightforwardly. And so we get a value of 2 times x squared y squared minus x to the fourth. So again, that is the value, that's the expression that the CDF evaluates to for points x and y that satisfy these conditions. Now, if y is between 0 and 1, but x is greater than y, then the CDF evaluated at such a point, x and y, is equal to the CDF evaluated at where y is both of the coordinates. Right? So we take that value of y and we evaluate, have the first argument and the second argument both equal to that value. And so when we do that, we plug we evaluate this expression here using those variables, then we get 2 times y to the fourth minus x to the fourth. We're plugging y in for x, and so that is 2y to the fourth minus y to the fourth, or 1y to the fourth. And then finally, if x is between 0 and 1, and y is greater than 1, then the CDF evaluated at x comma y is equal to the CDF evaluated at x comma 1, which is 2 times x squared minus x to the fourth. And so when we put these results together, we again have a piecewise defined function because we have to take into consideration which of the regions the point that we're evaluating the CDF at resides. And so we have these different expressions depending upon where the point resides in the plane. So that is the joint CDF. Now we're going to compute the probability that x is greater than 1/2 and y is greater than 3/4. And again, it really helps to draw a picture of the sample space, and then not only that, but the region over which we're going to be integrating in this case. So the region, that part of the sample space where x is greater than 1/2 and y is greater than 3/4. So to find this probability, we're going to integrate the PDF, the joint PDF, where x ranges from 1/2 up to positive infinity, and y ranges from 3/4 up to positive infinity. That simplifies to the double integral, where x ranges from 1/2 up to y. Y is ranging from 3/4 to 1. All right, so we can think of this outer integral where y is ranging from 3/4 to 1, and then for a particular value of y, x is ranging from 1/2 to that same value of y. All right, so you can see the calculations here. I'm not going to read through all these. You can pause the video if you want to work on this. But it's very similar to what we did before. And when you get through it, we get a probability of 119 over 256. So the probability that y is greater than 1/2 and that, that x is greater than 1/2 and that y is greater than 3/4 is 119 over 256. Now, we can also use the CDF to compute this probability, similar to how we did it in the previous lecture video. All right, and so in this case, the probability that x is greater than 1/2 and that y is greater than 3/4 is going to be given by 1 minus the sum of this expression here. So the CDF evaluated at 1, 3/4 plus the CDF evaluated at 1/2, 1 minus the CDF evaluated at 1/2, 3/4. And so we evaluate the CDF at each one of these 3 points, and then plug the values in, and we get 119 over 256. So again, we get the same exact value that we got when we obtained by integrating the PDF over the appropriate region. Okay, now we're going to calculate the covariance and the correlation of x and y. So we'll first calculate the covariance, and to do that, we're going to calculate the expected value of x times y. And so again, I can't stress enough how important it is to draw a picture of the sample space over which we're going to be evaluating to get these values. Okay, so again, we're integrating the function x times y times the PDF over the entire two-dimensional plane, and that simplifies to the integral of x times y times 8 times x times y over the region where y is varying from 0 to 1, and for a particular value of y, x is ranging from 0 to y. All right, and so then we can just go about evaluating this double integral in the usual way. We can bring out the constant. We can look at that inner integral and see that it does depend on y. Its upper limit of integration is equal to y. And so we have to integrate it in place. We use the fundamental calculus, the fundamental theorem of calculus to do that. And that integral evaluates to y cubed. And so we have the 8 over 3 times the integral of y to the 5th, where y is ranging from 0 to 1. And when we get to this point, again, we can use the fundamental theorem of calculus, and we end up getting 4/9. So the expected value of x times y is 4/9. The expected value of x, I'll let you take a look at this. You can pause the video if you need to. All right, but it evaluates to 8 over 15. The expected value of y, again, I will let you just pause and look at this. Make sure that you can work through it. All right, when you do this, you'll find that it's equal to 4/5 as well. So both, let's see, I'm sorry, I said as well. The expected value of x is 8/15. The expected value of y is 4/5. Okay, so the covariance of x and y turns out to be 4 over 225. Now, we're going to need to, now because, let me just say, because the covariance is not zero, all right, to find the correlation, we're going to have to divide the covariance by the square root of the product of the variances. So we need to compute the variances, all right? And so we're going to use the computational formula to get the variances, all right? And so to find the variance of x, we'll first find the expected value of x squared, that second raw moment of x. Once we have that, then we'll have both the first and second raw moments of x, and so we can use those to find the variance of x. And so I'll let you pause the video and work through this calculation. All right, we'll find that the expected value of x squared is 1/3. All right, the expected value of y squared is 2/3. And so now we can calculate the variance of both x and y. So the variance of x is the expected value of x squared minus the square of the expected value of x. So 1/3 minus 8/15. All right, and so we get 11 over 225. The variance of y is given by the expected value of y squared minus the square of the expected value of y. So 2/3 minus the square of 4/5, and that turns out to be 2 over 75. And so the correlation between x and y, which is the covariance divided by the square root of the product of the variances, turns out to be 4 over the square root of 66, which to 4 decimal places is 0.4924. So that wraps up the examples for this lecture. This video went a little bit long. I apologize for that. In the next lecture, we're going to start looking at marginal distributions.